Now, how do we derive this integral? We want to do a contour integral over this entire contour of d zeta x zeta zeta minus z. So this is what we want to do, and to do that we will first go around C naught. So we will have a contour of this over C naught. Let's call this L plus, and so L plus we go this way, L minus we go this way. So then we go around C naught, then we go along L plus, then we go around C, so this whole thing, and then we go around L minus again to get this entire contour integral. So this will be in two parts, out of which L plus and L minus are in opposite directions, so they are going to cancel. So this is L minus, so this and this are going to cancel out. We will be left with C naught and C. C itself is of two parts. One is along this circle, and the other is along this circle. So we will first go around the small circle, left circle. Then we will go from minus A to A. Then we'll go around the right circle. And then we will go from A to minus A. Okay. When we go from A to A, this function will become x plus. Here it is x plus on the plus side. So this would become dx x plus x into x minus z, which is exactly what we had set out to evaluate. Sorry, this would become x plus, I wrote it in the wrong place. This is x minus z, and when we come back along this will become x minus. This is the integral that we set out to evaluate, and as the radii of these circles tends to 0, we state without proof that these two integrals will also go to 0. So we'll be left with this and this. But remember, x is a solution to a homogeneous Hilbert problem. So x plus x minus beta x minus x is equal to 0, which means x plus x 1 by beta x plus x is equal to x minus x. Substitute that here, so I can convert it into x plus x and put a beta here. Let I be the integral that I want to find. I is the integral that I want to find, which is minus a to a dx divided by x plus x x minus z. This is the integral that I want to find. Then this is that integral. This is I, and this is beta times I. So the contour over C, this integral over C is equal to 1 minus beta of the integral that I want to actually derive, 1 minus beta I, which means I is equal to 1 by 1 minus beta, the integral over C of this function. So this is a result that I have. That is, I still have to evaluate the integral over C naught as the radius of this circle tends to infinity. So I'll have to evaluate this still. So this is the result that I have got. So the I that I want to evaluate is 1 minus beta times this. So now let us write the whole contour integral. We will remember that x we have already found as 1 by zeta square minus a square. So the function that we are evaluating is root over zeta square minus e square by zeta minus x. So the total integral now, the total contour integral is, these parts have cancelled out, is the integral over c naught and the integral over c. We have already seen the integral over c is 1 minus beta times the integral that we want to evaluate. So the integral over c is known. This is this integral we have already found is 1 minus beta times I of z. This integral we have not found out, but we know that the total contour integral, the result of the contour integral from the residue theorem will be 2 pi I times the residues of fz between c naught and c. Between c naught and c is basically this entire region. So in this entire region, the residue of this function has to be determined. That would 2 pi I times that would be the result of this entire contour integral, out of which this part we have already derived in terms of our iz. Now, if you look at this function, this has a pole of a unit order at z, and that pole, if you calculate the residue, apply the formula for the residue, multiply this by zeta minus z and find the residue, that residue is z square minus a square. So this is z square minus a square. So 2 pi I times z square minus a square minus this contour integral over that large circle will give me 1 minus beta times I. Okay, so this residue we know, and this is what we need to find now. Now let us calculate this integral over c naught. So this integral can be written, we can take the zeta below the a, and so this can be written as this by z 1 minus z by zeta. So this, to calculate this, we have to do it over that large circle. So on that large circle, zeta is equal to r e to the power I theta. We'll take r tends to infinity because we want that large circle to be far away, and then we do binomial expansions of this. So this is z by r e to the power I theta inverse. This one is 1 minus a by r e to the power I theta whole square, and square root of that. Both we can expand in terms of binomial. So this is the expansion of the minus inverse, and this is of the half. So here you will see that there's only one term which comes from multiplication of this with this, that will not have r e to the power I theta in it. All other terms will have r e to the power I theta in the denominator. So only this one term will contribute to this integral when r tends to infinity. All other terms that have r in the denominator will vanish as r tends to infinity. So when you write this term will be z, and this will be zi times, this I comes from here, this will be zi times d theta, which will give you 2 pi I z. So this integral over this big contour c naught, as the radius of the contour tends to infinity, is equal to 2 pi I z. So now I have everything. I have the residue of this. I know that this term is 2 pi I z, and therefore I have the entire so I now have the entire omega prime z. I just plug in the values. I have my iz, and if we integrate this, this will be my omega z. These are easy steps to do, so try them out yourself. P plus IQ is a constant. Remember, we have taken it to be a constant. It's same on the upper face of the crack and the lower face of the crack. Now, once you have this, then it is possible to get all the stresses in terms of this omega z, and that is why what we are going to do now. Theta z is 0, so there's only one potential that is needed to solve this problem, and to get the solution, what we are going to do is similar to what we did in case of the punch. So now for this crack, we will define one. So here's a point in space. So we'll define the coordinates point with one set of coordinates at this crack tip. So this would be r1 e I theta 1. Again, for origin center at this crack tip, you will have r2 ri theta 2, where theta 2 is this angle, theta 1 is this angle, and then you will have the usual from the origin, which is r e to the power I theta, theta being this angle. And for the first case, we will take that P plus IQ is equal to just sigma naught, where P is equal to sigma naught, which means that only a opening stress is applied on the crack faces, opening pressure is applied on the crack faces, and there is no shear component. Q is equal to 0. That's what we are going to do. So Z minus A is R1 e to the power I theta, Z plus A is R2 e to the power I theta, and Z is R e to the power I theta. Based on these quantities, we are going to express the various derivatives of omega z now. So omega z will be this, and this I have taken to be 0, no shear, and this is sigma naught. Okay, so this is the exercise that we are going to do. We can look at the terms one by one. Our idea is to find sigma xx, sigma xy, and sigma yy everywhere in the domain, and that we can do. First, let us start with sigma yy minus I sigma xy. We have seen that theta prime z is equal to 0. So sigma yy minus I sigma xy from km equations is this. Okay. Now we have done this for the punch. You can carry it out for this case also. So omega prime z has to be calculated in terms of R1, R2. We do it exactly in the same way as in case of the punch. So omega prime z is this. So your omega prime z is minus half sigma naught into 1 minus z by root over z plus a into z minus a. So in place of z, put r e to the power I theta. In place of z plus a, put r2 e to the power I theta 2, z minus a, r1 e to the power I theta 1. Right? And then you can express, okay, so when you do you have and you do it accordingly. So these I thetas will change to minus I theta when you have z bar. So z bar will be r e to the power minus I theta. Z bar plus a bar will be r1 e to the power minus I theta 1. This will be r2 e to the power minus I theta 2. And do the manipulation. If you do the manipulation, this is what you should get. This is what you should get. Okay, so then let us do this. So to do this, you have to calculate the second derivative of omega prime. First derivative we have, and you take the second derivative. The second derivative is this. Then do z minus z bar. Z minus z bar is, z is r e to the power I theta minus r e to the power minus I theta, which is equal to I sine theta, or 2I sine theta, I think, 2I sine theta. So this 2 cancels with this 2, so you have I, 2I r sine theta, sorry, 2I r sine theta is here, sigma naught is here, and then this part now you write in terms of r1 and r2. So this is the second term. This is the second term in the equation. Now you can write sigma x yy and sigma xy. So sigma yy minus sigma xy. We write it. So we can write it anywhere. We have sigma yy and sigma xy. So we have these quantities now in terms of r and theta, r1 theta 1, r2 theta 2. So we can write it anywhere for any value of r1 theta 1. But we are going to write it. So remember, this is the crack which lies on the x1 axis and goes from minus a to a. So this is a crack that has a finite size. It has a length of 2a, and it is subjected to opening pressures of this type. So it's sigma naught on the top and sigma naught on the bottom. This is the problem that we have solved. And this crack is a finite crack. It's not an infinite crack like in the Williams case. But we are going to look at now a small circle of radius epsilon with epsilon tending to 0 at the crack tip. And what we want to figure out here is what is the sigma yy and sigma xy on this small circle, and we expect that whatever sigma yy and sigma xy we get from this equation on this small circle should be similar to what Williams solution gave us in front of a crack tip. When you are in a small circle like this, you don't see this edge and you think that the crack is actually infinite. So Williams solution should hold if you are confined to this small circle of radius epsilon with epsilon tending to 0. So we are now going to calculate the stresses on a circle which is centered, let's say, at the z equal to a crack tip. We can also take a circle which is centered here at z equal to minus a crack tip, but we will first do it here. And if you do it here, then your R1 will tend to epsilon, R2 will tend to 2 times the crack length because the crack length is much larger than epsilon, R would tend to half the crack length, and theta would tend to 0. So so these are the things. Epsilon 2 will tend to 0 as well, and sine theta will be epsilon by a sine theta 1. And under these approximations, we can write down the entire stress and then use these approximations. These approximations will lead to expression for sigma yy and sigma xy, which is of this form. The real part of this will give me sigma yy. The imaginary part of this will give me sigma xy. If I extract the real and imaginary parts, this is what I will get. And if you look at these angular functions, you will see that these are exactly the same angular functions that we had in case of a mode 1 crack. Obviously, you imagine that this crack is being opened in mode 1. So for a mode 1 crack, whatever angular functions we had from the Williams solution are repeated here. In Williams solution, this angle was called theta. So Williams solution with an infinite crack with this as r, this as theta. In our nomenclature, we have a finite crack, but the other tip is very far away from this tip. We are very close to the right tip, and this for us is epsilon, and this angle is theta 1. So instead of theta, we have theta 1. Instead of r, we have epsilon, and you see that we have a 1 by root epsilon singularity at the tip, just like in the Williams solution. So these stresses are same as in the Williams solution, and now to so the only difference is now I know the stresses everywhere, and I have just used these approximations to find out the stresses on a small circle centered at the crack tip. Since I have the full field stress, I know the stresses everywhere, I do not any longer need a undetermined constant that we had from Williams solution, and which we called K1 for the mode 1 case. In fact, by using the definition of K1, which is limit epsilon tends to 0, root 2 pi epsilon sigma yy at x y equal to 0, using this definition for K1, I can actually find K1 from this equation. And that K1 would simply be sigma naught root pi a. If you calculate this limit, you will find that this the limit comes out to be sigma naught root pi a, which is the value of K1 for this particular problem of a Griffith crack, where you have a crack of length 2a in the center of a plate which is infinite in, and you are pressurizing the face of the crack with a normal pressure sigma naught. So K1 is as I said, it carries information about the load that you have applied, which is the pressure on the crack face, the crack geometry, and you have a value of K1 for this particular problem. If I had this load P plus IQ, and I made P equal to sigma naught, Q equal to 0, if I had done the other way around, if I made P equal to 0 and Q equal to tau naught, in that case, I would have a crack whose faces are being sheared, and that would be a mode 2 problem, and I can do the same thing, and I'll get the mode 2 stress intensity factor for this case, and that would come out to be tau naught root pi a. So what we have shown is, by solving the full field problem with Km equations, we were able to reproduce the Williams solution at very close to the tip of a crack. If we had taken the left crack face, we would have been able to do the same. So very close to a crack tip, the structure of the solution is completely universal. So this is the structure of the solution, and this Williams solution also told you that this is the structure of the solution. You have a root of epsilon or root of r singularity, and there's an angular function associated with sigma yy. This is the structure of the solution. What you get in addition for solving this full field problem is this quantity here, which actually gives you the correct form of the stress intensity factor. Williams told you that there is a stress intensity factor which will carry all information about load and geometry, but it does not tell you what that stress intensity factor is, what that particular factor is, what is the functional form of this. From a full field solution using the Km equations, we can get an exact form for a particular problem. We can get an exact form of the stress intensity factor, and we have shown that for the Griffith problem, it is sigma naught root pi a or tau naught root pi a in case of mode 2. So this is the power of using the Km equations, using which you can get the the stress intensity factor, the actual form of the stress intensity factor for a particular problem, provided you can uh, you can uh, uh, you can use the framework that we have set up here. And what does the framework entail? The framework entails an array of cracks, all on x-axis, collinear array of cracks, and each crack face loaded with a shear and a normal traction. Under this framework, if you can cast your problem in this framework, you should be able to get the stress intensity factors for any crack problem. And we have shown this for the Griffith crack problem, where you have a crack in the middle of an infinite plate. So let me stop here for the time being. In the next module, we will see that things can be simplified a little bit. And if your intention is to find the stress intensity factor from a full field solution, then you can do a little bit of shortcut. You still have to find this capital omega. You have to do capital omega prime and so on. Um, but things are slightly more simple if you assume that you are not interested in the fields very far away from the crack tip. You are just interested in the stress intensity factor, and you know whether the problem is mode 1 or mode 2. So for pure mode 1, the stress intensity factor can be somewhat easily found if you know omega prime. And similarly for mode 2, if you're sure that the problem is mode 2, you can use omega prime again to find the mode 2 stress intensity factor without worrying about the far field stresses. But obviously this solution, once you have omega prime, you must remember that the solution to stresses and displacements are known all over the specimen, not only close to a crack. So we need to know this solution in order to find the exact form of the stress intensity factor for a particular problem. Let me stop here. We'll carry on with the simpler technique, somewhat simpler technique, in the next